Hello there. Good morning, good afternoon, good evening, good night to all of you. Today, we're going to continue on with this journey of econometrics, and today the video will be on the topic of linear regression model. This is the topic that the video going to be this exploration of the linear regression model. All right, so let us move on with what is linear regression model, and we shall move on with the idea behind the linear regression model. All right, so the learning objective for this particular chapter is actually, hopefully by the end of this video, you could understand what's the idea of simple regression model, understand the logic actually behind the method of ordinary least square method, and some of the notation that is going to be used in this particular chapter. That focus in this chapter will be y is considered as dependent variable, x is the independent variable. So you have this kind of relationship, for example, like y equals to x and something. So this kind of a relationship that we going to explore in this particular chapter. The OLS itself is actually nothing new. You have done that in your previous subject, especially in the statistics, and when the lecturer of yours in the statistics discuss on the what we call as a regression model. We just make it much more comprehensive here in this particular chapter, right? So this is the notation or the terms that we're going to use here in this particular chapter, right? And by the end of this video, you can get some value added of what you understand, and if not, you can always pause, stop the video, and replay it again and again to ensure that you understand the thing, right? So we go back a little bit of historical. It sounds like a history of economic thoughts, especially because the history also important to be the good information, to be the information for the future. We learn from the history, and then we learn from the history so that we know what to do. So the history, the earliest form of regression was the method of least square, and this is nothing new. They've been around more than 200 years by these two legend name, Legendre and Gauch, in 1805, 1809. Both of them actually applied this method to the problem of determining from astronomical observation the orbit of bodies of the sun. And Gauch even published a development of the theory of least square in 1821, included the version of Gauss-Markov theorem, which we still use it until today as a basic of the regression function. The theorem there, we still use it today. Here, we also use it in any of the statistical related regression function. So that's the basic where that's starting from. So this is where they start off from. They look into the astronomical observation of the orbit from the sun. So they estimate such to explain such a phenomenon. And also this phenomenon, also this regression also been used by a person called Francis Galton, who actually used the term regression, right, to describe a biological phenomenon. What did he do? What does this person do? Actually, he looked at the phenomenon was the height of the descent of the tall ancestor tend to regress down towards a normal average, a phenomenon known as regression towards the mean. And this is what we are doing until today in the regression function. We regress based on the sample, and actually we find an average of those of the sample, and the sample is actually towards the regression is actually towards the mean. So the mean here, the average, is the important information for the regression function, especially. So this is the basic building blocks of where regression come from, how it's developed until today. And today we have a lot of type of regression, and what we're going to expose, what I'm going to expose to you in this particular chapter is the basic of the regression, which is called ordinary least square. In short, it's called OLS. Right. Also, is extended by the work of Yule and Pearson, and what we know today as Bayesian correlation and all those related to those. So since then, it has been used in a lot of research, including ours in economics and finance, especially, and it's applied to a lot of other fields. If you look into here, it was first adopted into astronomical observation, look into the biological phenomenon, also adopted into all the other research field today. So regression or statistical analysis in that particular sense have been used a lot in applied works, and that's what we're going to do also in this particular chapter. So what's the nature of regression? It's a tool used especially for econometric work. It allows the econometrician or the researcher actually to make a quantitative estimates of economic relationship based on economic theory. So that's where we come from. Right, still remember the like I told you, what is econometrics is the integration of the three particular field, right, of the we have a strong economics theory, mathematical, and statistic that's form econometrics. So the regression will provide the answer to this integration of these three subfield, and then it will can make the quantitative estimates. You get some estimates of regression of coefficients that can be explained, right? So you have dependent variable and independent variable for sure in that sense. So for example here, right? For example, you let's say you want to know what's the determinant of the salary, right? As a function of the movement in the set of other variable called explanatory variable: education, sex, age, occupation. Right? Salary, in the sense that salary is a function of all these variables just now. Says sex, age, and occupation. Does the sex or the male and female matters in terms of salary? Does the age matters to determine the salary? And does the occupation determine certainly the salary in this case, right? So those are the variables that we're going to use. And this is, if you have just one x and one y, this is called simple regression. You have more than one x, we call it multiple regression, where you have multiple independent variable or explanatory variable. So what's the aim of regression? This can be a very good the objective of your study for this project, for this class, or for your FYP later. Why? You can always adopt this as part of your objective to examine, to analyze, to forecast, if that is your objective, right? So you have three objectives already for your and it can be put under research method too, to examine certain things towards certain things, certain variable towards this other variable, to analyze the effect of x towards y, to forecast the value of y for a given set of x. The x and y here can be your specific variable. So it can be a very good objective, not just the aim of the regression. Right? Think about it. Right? This is what commonly used terms in terms of x and y. Right? In terms of x and y, they've been used in that sense. Normally been used in the regression function. So it can be this is the y. This part is y. This is y, and this is x. All right, and this is the other variants of the names. It can call regression. It can call dependent variable, called predictant, called effect variable, called endogenous variable, called target variable. It can call regressor, independent variable, predictor, x. Causal variable, exogenous variable is x, endogenous variable is y, control variable is x, certainly, and y is the target variable, what you want to target. Let's say the target variable is the GDP. The control variable is all the other variable that going to determine GDP itself in a country, right? So to know further, we have to know the differentiation or the difference between regression and causation. What's the difference? Regression analysis deal with dependence of one variable on the other variable, right? But it does not necessarily imply causation. For example, this is the example here. A statistical test established that the more a person smoke, the greater probability of developing a lung cancer. Greater probability. However, the analysis do not prove that smoking causes lung cancer. Not on statistical point of view. Not on statistical point of view. This should be on medical investigation. You want to know medical investigation, further medical investigation, then you need to go further to ensure that when a person smoke that much, the person can develop cancer, lung cancer in this case. It's the same thing as what we have, as what the pandemic today, right? I mean the SOPs, governments around the world, and endorsing or believe that the SOP, social distancing, is one of the common SOP that adopted by the whole world. Using masks, make sure we mask on, and social distancing. Why? Because if we wear the mask and we have social distancing between individuals or the people around us, then there's a lower possibility of getting infected by the coronavirus, right? Those are the probability, right? Probability of developing the or infected by coronavirus. But it doesn't prove that while not wearing a mask or not having social distancing, it will cause the COVID-19. That one have to prove it through the test. That's why a person, although is a close contact, or suspected close contact, that particular person or that particular group of people have to go through the swab test to prove that the person are infected by the disease, by the coronavirus. But statistically it's proven that the social distancing and the mask could lower the probability of the infection, right? So that's the meaning here. Regression versus causation is different from causation in that particular sense. Regression versus correlation is also two different things. Regression, it means that y is a function of x. Y means that x determine y. So that is regression. But correlation, the correlation between, for example, here, for example, given this example, for example, we may use correlation analysis to find the correlation between education level and the salary of the Bachelor of Economics graduates. Means that all of you here and those in this faculty, in fact, the generalization in that sense, whether education whether the education level that you're having now and the degree level, the first degree level, going to affect the salary that you're going to receive when you graduated. So we can do a simple correlation analysis, but it's not the same as if you do regression. Regression in this sense, for example, I put their salary and then education represented by E here. All right, this is regression 1. This is regression number 1. Let's say I have another regression, which is education here, and the S is here. So you get two different results from the regression, but the correlation between salary and education, either way, A and B or S and E and S are the same, right? So two variables are treated symmetrically in fashion when there is no distinction between independent or the dependent variable, right? But not in regression. So this is the two important elements inside there. So in the basic ordinary least square or the regression function, we're going to specify the model based on the suggestion, based on the chapter number 1, where we want to do the so-called analysis. You have to go step 1, step 2. This is considered like a step 3 or 4. You're going to specify the model, right? How are you going to specify a model? We still use back a simple demand function. This demand function here, yeah, this demand function, this is the demand function which included the error term, which is the econometric function or econometric model here. Here is a demand function in terms of functional form. You can write it in a mathematical form also. All right. We need to extend the deterministic model by including a random terms that measures the error of the deterministic component econometric model, which is this. So here is deterministic. Why is called deterministic? Because you can determine with this additional thing, random terms or the error term, then this regression becoming econometric model or empirical econometric model and the general empirical econometric model, and it's become a random model, an econometric model we call it. For example, like this is a simple example to study the relationship between the two variable consumption and disposable income, which is important. Consumption means that income affect consumption. The higher of the disposable income, the higher going to be the consumption, right? We plot a scatter diagram like this. Imagine this scatter diagram. I'm going to connect them. I'm going to draw them. This scatter diagram is actually the real plot of these two variables, and this actually represent the real function. This straight line represent the linear line, which is represented by the regression line. In that sense, represented with straight line, but the original line, the dotted line, when we plot these two y and x together, you get this dotted line, which is not a very straight line. So one of the best way to estimate this crooked line, I would name this crooked line up and down here, is to determine the best fitted line, which is called the least square method. So the best fitted line is the one that the straight line that we understand, right? But the original line are not as straight as that. But it's okay because that's the best we can represent it in that sense. This resulting line is known as the least square line or the regression line, whereas the equation that represents this linear regression is called linear regression model. This is where this linear regression come into picture. We want to find the relationship between X and Y, in this case consumption and disposable income. But we know that when we plot the graph like here in this figure 1, is not a straight line. But our assumption of the linear regression, which we go through the next chapter, it's talking about the linear relationship. So to ensure that they are actually a linear relationship, then we have to use a straight line like this, the linear function like this, and ensure that this is what we call as a linear regression function or linear square, least square method in that sense, right? To represent this thing, right? What does that mean? What is actually does that mean? What does least square and linear regression means? Linear refers to linearity in the variable. So this is linear, this is non-linear. We're not considering this model inside there, even though this might be the variable, but in the end we linearize the non-linear relationship. We force them to be linear, in other words, trying to say that. And the parameters are actually linear too. This is the variable, right? The variable are linear, the parameters are linear too. All right, in this sense. The parameters in this sense, the variable in this case is the x and y, the parameter in this case is the alpha and the beta, also are linear. You see here? The beta square, so the x square is the non-linear function. So variable is the x and y, linear, and the alpha and beta are also linear. All right, this is the explanation on that. So this is the simple regression with one x. This is the multiple regression with more than one x. It can be x1, x2, x3, x4. Multiple regression, you can imagine, for example, the simple macroeconomics function where y equal to c plus I plus g, right? You can finish up the equation. Ci g x m. That's the example of multiple regression. Simple regression will be like this just now. This is the simple regression x and y only. One x and certainly one y. There's no more than two y. Not more than one y. Certainly, right? There's always have one y. Here, the extension is here. All right? So that's the idea behind. When it's simple regression, we need to find the in this sense to find the x, the coefficient of the x, which is represented by the parameter beta in this sense, right? So then we know the kind of relationship. We know whether what types of relationship, what types of whether they're positive, negative, and so on from the estimation. All right, so we're going to estimate the unknown in the stand the multiple regression, the betas, we said more than one betas are the coefficient to be estimated using regression, right? And betas are thus known as the regression coefficient in this sense, right? You can calculate the simple. This is the simple this you will know the slope or the simple slope of this regression, right? Here you can simply calculate this, and this is not new also for most of you. You can remember what you have done in your high school, your secondary school. Y equals to you have to remember this, mx plus c, right? Mx plus a c is actually similarly to this regression. I can see this function here. See, it's still y. The mx is this part, the beta x here. The c here is considered as a constant, right? So it's as simple as that. And you have done that actually. We have done that actually in the secondary school. And this is the extension and explanation. What's the meaning behind? What's the quantitative meaning behind? And how we're going to use that to explain a phenomenon in terms of academic research, in terms of economic research or finance research in that particular manner. All right, so then we move forward to another terms to introduce to you this regression function, the linear regression, and so on, which I mean related in that sense, to know what is deterministic and what is stochastic. Stochastic is actually can be referred to random. Deterministic is exact. Stochastic is statistical relationship which does not give a unique value of y for the given value of x, right? Certainly you use a lot of probability terms in statistical regression, use statistical model. So this is deterministic. If we know x, we can solve y, or you know y, you can solve for x. Simple as that, straightforward. Here, yes, you know x, you can solve for y, but still with these terms. This is the error term, right? This is the probability, the uncertainty, the stochastic relationship. But the question in mind, maybe some of you have in mind, is that what the heck that we have to put something stochastic in this model? Why not just make our life easy and do a kind of a simple mathematical relationship like this? This is mathematics. This is mathematics, and this is statistic. That's the two different between the both mathematics and statistics. All right. Why add an error term? Why the heck that we want to add the error term? This one, based on the last our discussion in chapter number 1, especially why need to add a stochastic error term? Because for certain particular reason, because of economic variables are unlikely to be exact because stochastic error. So that's why we put in the stochastic error inside there, so that it can represent something that is not there, not the exact relationship. Like maybe for example, I give example. People ask, I mean, some of your friends, your family members, your parents, in fact, maybe ask you, what going to be the forecast for next year economy or this year economy 2021? Can you answer it specifically? Oh, the forecast this year is 3.0 growth rate. How you know 3.0? That is not an exact value, except that you have the data and so on. You come out with that figure. If not, if you come out with just a figure from your mouth, that is really not a good I mean, that's not doing research. It's just come out for the mouth, and it's not reliable. So why add an error term? Because disturbance or error term must be included in the exact relationship postulated by economic theory and mathematical economics in order to make them stochastic. in order to reflect the real world. Economic relationships are inexact. There's a lot of uncertainty. There's a lot of things happen. Shocks happen. Like this pandemic. It's been going on for a year. How is impact? Yeah, by now maybe a lot of journal articles have estimates. Estimates, right? The word used is estimate the impact of the pandemic crisis towards certain sectors and so on, right? Or if you're in sales, I always quote side sales. You do a forecast for next year's sales, a forecast and estimate, not the real value. All right. So this is what happening. To account for inexact relationship, then we include this error term or this error term in this sense. Right? Econometric also admit the existence of such unexplained variation but explicitly include the stochastic component in the model. So that's why the inclusion actually, because the economics relationship itself is such an inexact. So these are few reasons behind. Justified also consideration of the net effect of the possible error measured by dependent variable or using dependent variable being explained, in other words. All right. Since human behavior or the is inexact or erratic in that sense, then we include the error term to represent such a stochastic behavior. All right, and so on. Error term also represented. It can be a good representation of the variable that you are not putting into the model. All right, and the relationship by certainly by economics theory and mathematical economics in this sense. So, example, this is the model. This is the true population regression function. In short, we call it PRF. True model. Population is the true model. Right, but what we are estimating is the sample SRF to represent the PRF. Right, SRF to represent the PRF. We use sample to represent population. So the idea here is that you must have large enough sample to represent the population. You can't use a small sample for the population. For example, if you look into time series here for the country, for Malaysia, we know that Malaysia have been independent since 1957 and or 1963 in that particular sense. So it means that the data should exist by then until today. So if you're just doing estimates of 1990 until today, it does not represent the whole population, right? Same thing goes to if you want to do a research on perception on UNIMA student and you use FEB only as the representation for the population of the student here in the university. That is not good enough, right? That is for a cross-sectional kind of study and time series, as I mentioned just now. So given the SRF, the sample regression function, it should be a good approximation of the population regression. The nearer the better, the larger the better, the sample. All right. So this is the sample regression function, and this is the population, the real true regression function line, and this is the estimate line. The dotted line is the estimated line. The true one is the blue line, which we're going to try to achieve in this sense. Right. So we're moving on into the few of the last slides for this particular chapter. Talking about ordinary least square, what's the meaning of ordinary least square? Move on the ordinary least square. It's actually OLS, or the least square methods, is actually minimizing sum of square residual with respect to the alpha and beta. Right? We do partial differentiation, which all of you have done in your mathematics with respect to the coefficient, and you get this kind of first order condition like this. Right, to calculate the alpha and the beta. Solving it, you will get this kind of relationship. Solving one or two simultaneously, no worries, we're not going to prove this because this has been proven. You just have to use it. Right, this is the calculation for the coefficient of beta. This is the calculation for the coefficient of alpha. If let's say you have simple regression. If you have more than one beta, then this will be much more complicated in that sense. Not really complicated, but This is or what more important is that the method of least square is minimizing sum of square residual. That's the more important thing. All right, that's for now. We have not yet finished up. Let me share with you this one. This is from the book from the book called Econometrics for Dummies. It's available in your ellipse. You can find this. You can refer to chapter number 4, which is very much interesting. Chapter 1, 2, 3 is actually based on the early chapter of chapter 1 and 2 and 3. You can read this book, although this is not a textbook, but this is a very interesting, easy book to read. It says that in this chapter, understand the difference between correlation and causality. We have done that. Building econometric model and make a case of causality. This is extra thing. Extra above from what we have discussed here, working with different types of economic data. So this is more interesting. I just share with you some of the justifying of what we are doing. So same here, you see here, this is pretty interesting, right? This is pretty interesting to explain a certain phenomenon, especially, right? Let me make this thing much more bigger. This is to explain causation cannot be proven by statistical result. Your result can be used to support hypothesis of causality, but only after you develop a model that is well grounded by economic theory and a good common sense. In that sense, this is the plot of ice cream and the drowning. How does ice cream consumption related to drowning? Drowning, lemas. So interesting. Does it proven any relationship? It seems like have some relationship in this sense, but we must have certain types of economics theory behind to prove such a thing. So this is PRF, population regression function, right? As already discussed, here you have a general mathematical model like this one, this function here, general mathematical model. And then after that, you still represented by the econometric model, you added up the error term, right? Added up the error term like this. Random nature of your model, added up the error term becoming random, right? So then you can estimate the regression and provide some estimates based on that, right? This is several examples that you can have a look of this book. Right? This is another example, right? Let me not go through further of this one because this is something beyond this chapter, but we're certainly going to discuss this, and you can always refer to this book. It's a good book to read. We ended up here, like, all right, we're going to ended up this particular chapter, especially when we already talk about the particular book just now on this building block of this book of econometrics for dummies, and then we ended up this chapter number 3. But end up, you can see one of the examples which I'm going to explain in the online class, especially on the example that talks about this OLS example. Right. Other than that, I will stop this video here in the chapter number 3. Take care, everyone. Stay safe. Adios and bye bye.